let's start. And we've got, we're going to start from the last question, which is this one, that it's saying that there's a compound T is made by 3-stage synthesis. Stage 1 is whatever this is. It reacts with a suitable reagent to form compound R, this one. So basically what is going on over here is that the OH over here, so your OH is getting substituted by Cl. How do you do that? It's PCl3 plus.
Or SOCl2, could be anything.
Or SOCl2 plus heat. Okay, that's 1 mark. Here you've got in stage 2, compound R reacts with ethylamine to form a compound S, which is this one. So remember this thing. Amides are formed. I mean, that's an amide in stage 2. Name the functional group formed in stage 2. That this over here is an amide. Okay, remember this. Okay, amides are formed by acyl chlorides. And we did this over here when we did esters. We did when we did polymerization. That's addition. Anyways, this one. So remember, polyamides are formed when you have an acyl chloride reacting with an amine, and that would result in the formation of amides. So this is that reaction. Identify the other product formed in the reaction. So what happens is, in this case, what happens is the Cl is lost and the H is lost. They're going to end up forming HCl. So HCl is the byproduct of this reaction. You're going to get HCl. So the amine N will join with this carbon atom. Now we've got another reaction, reacts with a suitable reagent to form compound T, which is this one. That is the reduction of amides. So this one is reduction of amides. This is this part. Okay, you've got where is reduction? Just a second. So reduction of amides. That if you have an amide, it gets reduced to an amine. The double bond O gets replaced by hydrogens with LiLH4. So this is state the suitable reagent, that's going to be LiLH4. And in the type of reaction, that's going to be reduction. And then you have the relative, this is the M+1. Calculate the relative abundance of the M+1 peak in the mass spectrum of ethylamine. So he's talking about the relative abundance. The relative abundance of the molecular ion peak in the mass spectrum of ethylamine is 62. Now, first thing, what was the formula of number of carbon atoms? It was 100 over 1.1 into M+1 divided by the M height. Okay, now in this case, you know that ethylamine, the number of carbon atoms, it comes out to be 2. So it's 2 is equal to 100 over 1.1. The M height is given, that's the molecular ion peak is given as 62. So that is given, and you just have to figure out the M+1. So you can try and calculate this. Can anyone try and calculate this? What do you get for this? It's going to be 2 times 1.1 times 62 divided by, I think, 100. What are we getting for this?
$1.364.
So we're getting 1.36. So we are getting 1.364. I'm just going to double check this. What do we have in the marking scheme for this? It's the last question. So we just had to use the formula in reverse, and that is coming out to be 1.36. That's exactly what we got. So 1.36, 4 rounded off to 1.36. Then you have the mass spectrum of compound T contains several fragments. The ME value of 2 of the, he's talking about T. Let's go back to T. This is T. So he's talking about the fragmentation. Fragmentation is that the molecule, it's any small piece of this bigger molecule. That's what a fragment is. So that is one example. So he's going to ask you about identifying those fragments. So he's saying that there's a peak at 29. So what could be 29? There's a peak at 91 as well. So you're getting two fragments, one at 29, the other one at 91, and you have to identify the two fragments. So try and identify what's 29. 29, I think, is I mean, that's.
So how do we find this molecular? वो पिछला क्वेश्चन जो आपने किया ये 1 mark वाला
Number of carbon atoms का formula पता है? It's the number of carbon atoms is 100 over 1.1 into m plus 1 divided by m, right? Okay.
Yes, sir.
Is this clear?
जी sir. Yeah.
So what we did was, okay, I know it's ethylamine. I know that the number of carbon atoms is 2, right?
2.
So and they gave me the molecular end peak, the M peak. Its value is 62. So I put that as 62. So I figured out what m plus 1 was using that.
Sir, do we have mass spectroscopy in the syllabus?
If we do have mass spectroscopy in the syllabus.
No, I've compared the syllabus and they removed it. We just have NMR of carbon and proton.
It's in AS, but it's going to come. It's going to come in. I mean, it's this one, right? It's so they've removed it from A2. They've taken it to AS, but the thing is that it's something that's kind of basic, so it's probably going to come. Like if you, so this section is now in AS, but a lot of questions would have this. I mean, it's not it's very easy actually. It's you just have to figure out. You can figure out the number of carbon atoms if the m plus 1 m peaks are given, and you can figure out the number of chlorine and bromines if the m plus 2 peak is given. So somewhere in the question, because they will give things from the AS syllabus as well. So you have to be prepared for this. Is that clear? So this one. So 29, let's talk about 29. 29 is, it's probably going to be this piece. It's going to be CH3. It's going to be CH3 CH2 fragment. If it breaks off, that will have a mass of 29. That's 24 plus 5, that's 29. So the structure of the ion would be, and it will have a charge of +1. And then there is a 91 as well. So what could be 91? That's slightly more difficult. So this is 29. How do you calculate 91? This is C6H5. Can anyone tell me what the mass is? Like 12 into 6. That's 72.
That's 77.
77. So up till this point, it's 77, right? You add 14, you add 1 carbon and 2 hydrogens to it. So 77 and 14, that's 91. So it's probably this fragment over here. So this is going to be 91. This one. A benzene with CH2. So that's C6H5 and CH2. That is your fragment. That's 91. Now you've got, is that clear? So we figured out the fragments of the molecule that had a mass of 91 and 29. Now you have got an H&MR spectrum. The compound T shows hydrogen atoms in different environments. 6 of these environments are shown on the structure using letters A, B, C, D, and E. Okay, that's fine. Use letters A, B, C, D, and E, F to answer the following. The questions relate to proton NMR spectrum of T. Proton D does not cause splitting of the peaks for proton C or E under the conditions used. So proton, I mean, we did talk about this one, that NH protons and OH protons, they don't cause splitting. And they're always singlets. What is the splitting rule? That it's the n+1 rule, that if the neighborhood has n hydrogens, there would be n+1 peaks. So identify the proton or protons with a chemical shift in the range 6 to 9. So for this, we would need to open the data booklet. I think at the bottom there's, so 6 to 9, where is infrared? This is, so yeah, NMR. So this one, 6 to 9. 6 to 9 is this range. That's a hydrogen proton on the benzene ring attached to the aromatic ring. So that will resonate at frequency 6 to 9 wave number. That's, sorry, chemical shift. So which one is this 6 to 9? That's A, right? Is that clear?
Yes, sir.
And identify the proton or protons whose peak will disappear if D2O is added. Remember, the NH2 and OH peaks, they, I mean, these are the parts of the molecule that ionize. So when you add deuterium to it, these two get displaced by deuterium. So the D peak is going to disappear. You can always remember that NH and OH, they like to ionize. And they might, in D2O, in heavy water, they would get displaced by deuterium. So they would disappear. Identify the proton or protons whose peak is a triplet. So first one, this one has 3 H's, while this one has 2 H's. What would this peak be? F, would it be a doublet or a triplet? The neighboring carbon atom has 2 H's. So what would it be?
Triplet.
Okay, that's going to be a triplet. What would this be? E, the neighboring carbon atom has 3 H's.
Quadruplet.
Quadruplet. Okay, that's a quadruplet. And NH does not cause any splitting. So anyways, he was asking for the triplet, so that was F. So this was F. And the last one is identify the proton with the lowest chemical shift value. So the lowest, or the lowest, what does lowest mean? Smallest? With the lowest chemical shift value. That is, I think, F, because the lowest you go is 1. You actually do have this one. The lowest one is, I think it's the carbon chain one. It's 0.92, 1.7. So that's the lowest. So the one that belongs to the carbon chain, it's this one. I think it's F. So I'll just double check, because number 4.
There aren't B and C triplets as well?
B and C? C is definitely a triplet. Okay, B is going to be a triplet as well, because the neighboring carbon, I mean, this carbon does not have an H, right? This one does not have an H. So it's this one, the neighborhood has 2 H's, right? So both of them would be triplets. I mean, this one, the neighborhood has 2 H's. This one, the neighborhood has 2 H's as well. So they're both going to be triplets. Anyways, I'm going to just check the last one, which is, the last one is F again. So sorry, the previous one was B, C, and F. So we had to identify all the peaks. I just identified 1. So it included B and C as well. Okay, Basa, you were right. These two were also triplets because the neighboring carbon atom had 2 H's, 2 protons. So is this question clear?
Yes, sir.
So now let's move to question number 8. Now this is about basicity. There's 2 amines state what is seen when aqueous bromine is added to phenylamine. So that is.
Sir, we didn't do question number 10.
No, there is a question number 10. 1 second. Sorry, there's a question number 10. Sorry. This is about valine and lysine amino acids. The structures of those amino acids can be found in the data booklet. The isoelectric point of an amino acid is the pH at which it exists as a zwitterine. The isoelectric point of valine is 6. The isoelectric point of lysine is. Draw the structure of valine at, first thing, what is valine? That's an amino acid. It's a carboxylic acid plus it's an amide. And there's an R group. For valine, I need to figure out what the R group is. So these are the needed. That's on the amino acids once again. So over here, are these the amino acids? No, that's just the amino acids. One second. No, from now on they'll probably give it. If they give you an amino acid, valine is, I think, 3-carbon chain. It's a 3-carbon atom chain. This is the older data booklet. So this one has amino acids, this one. So valine is CH with 2 CH3 branches. So we go back. So it is CH with 2 CH3 branches. Now, the first thing I'm going to explain is what is the isoelectric point. Remember, one part of an amino acid is acidic. I mean, this part is acid. The other part has lone pairs, and that is basic. That's a base. What will eventually happen is, what is a zwitterine? A zwitterine is that the carboxylic acid loses the H plus when it turns into a -1 ion. And the base over here, the lone pairs, they end up accepting H plus 1 ions. Right? So that is what a zwitterine is, that it has negative charges and positive charges, but it has no overall charge. So is this clear what a zwitterine is?
Yes, sir.
Yes.
So now the thing with zwitterine, now I'm going to tell you what an isoelectric point is. So let's imagine a zwitterine usually exists somewhere around pH 7. I mean, this happens. A zwitterine happens around pH 7, not exactly at 7, but somewhere around pH 7. If the solution is too acidic, right? So let's go back and let's assume that the solution is very, very acidic. And you had an amino acid, right? So you had an amino acid, and let's get the H back. So if the solution is very, very acidic, that means there's a lot of H plus 1 ions. So what will the amino acid look like? Will this be able to lose H plus 1 in acidic environment? It would probably not be able to do that, right? But the base would still be able to accept H plus 1 ions. So in that case, this side would become positive ion and the other side would not be able to lose H plus 1. Is that clear?
सर तो फिर ये NH2 होना चाहिए.
Yes, sir.
क्या होना चाहिए?
I mean, अगर positive charge अभी भी NH3 पे है तो फिर I mean, how is it accepting proton या क्या हो रहा है?
नहीं, पहले तो it was an amino acid, right? It was NH2, but it had lone pairs, right? So if the solution is too acidic, then it would accept H plus 1 ions, right?
Okay.
And it would become NH3 plus 1. Is that clear?
जी.
I said now vice versa. If the solution is too alkaline, so in that case, the amino acid would look something like this. The NH2 would not be able to accept H plus ions because there is no H plus ions. There's OH ions around it, right? So the base will not be able to, but the acid part, the acid would still be able to lose H plus 1 because its H plus 1 will get attracted to the OH minus 1. And so the acid part would still be able to lose H plus 1 and it would become negatively charged, right? So So in acid environment, the base gains H+1 ions in basic environment, the acid ends up losing H+1 ions. So this side becomes negatively charged. Somewhere in the middle, somewhere down in the middle, like at around pH 7, where there's equal quantities of H+1 and OH ions. Let's say there are 3 H+1 ions. Let's bring the, and on this side there's 3 OH ions. So that is kind of neutral solution, right? In neutral solutions, the amount of H+1 and the amount of OH ions is equal, right? So in this case, a zwitterion would be possible, that the N over here would be able to gain H+1 ions, and the H over here is able to lose H+1 ions, right? Is that clear?
Yes.
Yeah.
So a zwitterion is going to be formed around pH 7, but not exactly at pH 7. Sometimes what will happen is we want the NH2 to gain H+1. So maybe it's a strong base and it very easily gains H+1 ions and it turns into NH3 plus 1. But I want that one to lose H+1 ions, but maybe that one is a weak base. So if it's a weak base, I would have to make the solution slightly more alkaline. I would have to add more OH ions so that it's able to lose the H+1 ions. So, and it would become negatively charged. So the point I'm trying to make is the two things, the base and the acid over here, they don't have equal strength. So since they don't have equal strength, so the zwitterion is not always going to be formed at exactly pH 7. Sometimes to make a zwitterion, you would have to make it slightly more alkaline. Maybe the acid is not willing to lose H+1 ions, so you would have to make it slightly more alkaline. Maybe the base is weak base and it's not gaining H+1 ions, so you would have to make it slightly more acidic. So is that point clear as well, that the isoelectric point is usually not always at pH 7? Is that part clear?
Yes, sir.
So, but you're going to treat your isoelectric point as pH 7. I mean, you're going to treat it as if it's pH 7. Like, if the pH is above the isoelectric point, you're going to think of it as the solution being too acidic, alkaline. And if the isoelectric point is below, if the pH is below isoelectric point, I mean, for example, if for valine it's pH 6, right? So you're going to take pH 6. That is where it's a zwitterion. If the pH is greater, then you're going to think of this as the solution being too alkaline. And if it's below pH 6, you're going to think of it as the solution being too basic. So there's going to be one, I mean, the zwitterion will not exist if the pH is above 6 or if it's below 6. Is that part also clear? So, for example, I've got valine over here. He's saying it's 6, and now he's saying draw the structures of the. Wait a second. A solution of lysine is produced with pH 9.7. A solution of lysine, dilute sulfuric acid is added slowly until the pH of the solution is 1. The solution reacts. The sulfuric acid reacts with lysine. Sorry, the first part was draw the structure of valine at 6. That would have been a zwitterion at exactly 6. It's this one. Then he's adding sulfuric acid. The sulfuric acid reacts with lysine to produce different organic ions that are not present in significant concentration at pH 9. Now you've made the pH too acidic. And he's talking about lysine over here. Draw the structure of the 3 of the organic ions that form during the addition of sulfuric acid in the boxes. Draw the organic ion present at pH 1 in box C. So, firstly, you need to know what lysine is. Let's go and have a look. Lysine is this one. The carbon chain is this big carbon chain with NH2. So that is what lysine is. So it's an amino acid with an NH2 group, and it's got 4 CH2s. And then at the bottom, there is NH2. And then you've got an H. Now that's what lysine is. So sulfuric acid is added slowly until the pH of the solution is 1. So it's highly acidic. If it's highly acidic, you've got NH2 over here and you've got NH2 over here. This molecule has, so it's got 2 lone pairs or 2 basic groups. So one thing that would be formed is either it's going to be, so what are the 3 ions that are going to be formed? Either this NH2 ends up gaining H plus 1. You guys are
What happened to B? I mean, how did you draw B?
Sorry, I don't know it's B or at the moment. Okay. The point I'm trying to make is that he's made the solution very acidic. So NH2 over here will gain H plus 1 ions, right? Or it could be, I'm going to come to A and B, or it could be okay, the bottom NH2 that ends up gaining H plus 1 ions. Or the third one that's possible is both of them end up gaining H plus 1 ions because you've got 2 basic groups. So this one gains H plus 1 and the other one also ends up gaining H plus 1. So he's saying draw the structure of the 3 organic ions that are formed during the addition of sulfuric acid. So first, either one of the H plus 1 gains, so that's 2 ions, 2 different ions, and that's probably the third ion. To get pH 1, that's extremely acidic, so both of them would end up gaining H plus ions. So I think that's this one.
So yeah, how did you figure out these structures?
Yeah, I know okay, he's making the solution very acidic, right? Okay. So if he's making it very acidic, so in acidic environment, what happens? The basic group ends up gaining H plus 1 ions, right?
Yeah.
G.
And then when we drew the molecule, we figured out that it had 2 NH2 groups, right?
Mm.
So
Sir, ये lysine का structure है, by the way.
हाँ, वो data booklet में है ना, it's given over here. Okay, the lysine R group is this one.
Yeah, ठीक, okay.
So anyway, so either this one would gain H plus 1 or that one would gain H plus 1 or both of them would gain H plus 1. So I'll just double check this one. I don't know which one is A and which one is B. So I think it's the same. It's either this one gains H plus 1 or the other one gains H plus 1 or both of them gain H plus 1. So that's the final one. And there's a third one also given, I think. What is this? And isn't this exactly the same as, what's the difference between, actually they've C at pH, this one, they've also, one of them, they've lost, the acid has lost H plus 1 ions.
And the other one it didn't lose.
So any 2 from these 2, okay, fine. So we didn't draw this one. And pH 1 is this one. So fine. We didn't draw this one, but still we got full marks. And draw the structure of dipeptide valine and lysine. That's I mean, valine is going to come first, so it's C double bond O. OH, there's an H and an NH2 on one side. And there is a carbon, valine is CH with 2 CH3s. And the other one is lysine, it's CH, C double bond O. And you've got NH2 and 4 CH2s. And there is 1 NH2, okay, that's from the data book. So the H and OH would be lost from the middle. So that is gone. And you're going to have an amide or peptide bond which we have shown, and he has said that draw fully displayed version of the peptide bond only. So we've done that. Okay, so remember this, you don't have to remember the amino acids. The R group of the amino acids is given or might be given this time along with the question. So what else do we have? This one is about phenylamine. What happens when you add, when you do bromination of phenylamine? So that is electrophilic substitution. So when you do bromination of phenylamine, the benzene ring is highly activated. Why? Because the lone pair on N mixes with the benzene electron cloud, making it increasing its negative charge density. So when you do Br2, it gets added to all three positions, and that results in a white precipitate. Let me add that. So sorry. So board is hung up. It's so anyways, this it's still hanging up. So let's still hang. Wait 1 second. So the first one, state what is seen. That's a white precipitate. That's this one over here is a white precipitate. Suggest what is seen when aqueous bromine is added to ethylamine. I don't think anything is seen. When aqueous bromine is added to ethylamine, nothing should be seen. Like there is absolutely no reaction. Draw the structure when aqueous bromine is added to phenylamine. So phenylamine is this thing with NH2, and bromines will get added to positions 2, 4, and 6. And name the product you've drawn. That's tribromo or 2,4,6 tribromo phenyl amine. Okay, that's 2,4,6 tribromo phenyl amine.
Sir, thin positions पे bromine banana, I mean, is this necessary, or can we just make it bromine?
In this case, it's highly activated. So it's better to actually draw it on all three positions. I think I'll just check. Okay, over here, what question was this? All three is, and 2,4,6 tribromo phenylamine. So all three. And question number 7 is give the number of different peaks in the carbon-13 NMR spectrum. So look at the carbon environment. So this carbon is unique right? It has a different environment compared to all the other ones. These two carbon atoms are exactly the same environment. Then you have these two carbon atoms, they're exactly the same environment. You have this carbon is unique. Similarly, this carbon atom is different from all the others. And finally, you've got this. So these two, so how many different number of peaks? That's 1, 2,
6.
3, 4, 5, and 6. So you've got 6 peaks. And ethanol behave as acids. Compare and explain the relative acidities of ethanol, phenol, and this one, phenyl ethanoic acid. So carboxylic acids are the strongest one. So that's if I call this A, this one goes over here, which is obviously phenyl and ethanoic acid. And alcohol.
Least acidic.
Sorry, I mean most. Let's make it most acidic.
Yeah.
And the other one is ethanol is the least acidic. Normal alcohols. Phenols are somewhere in the middle. So you just have to describe why alcohols are such terrible acids. So you're going to describe that. You're going to talk about the electron donating effect of the alkyl chain. What does it do? That if you have ethanol and the ethanol dissociates, then the ion becomes unstable. This ion becomes unstable. It has a greater charge density. So it's not going to let go of the H+1 because it's going to get attracted to the H+1. And you can talk about the ethanoic acid, that there is an electron withdrawing group, which is basically Cedal bond O, or the electronegative oxygen. So what it does is that when the carboxylic acid ionizes, the negative charge density decreases and on the ion, and it becomes stable. So it no longer attracts the H+1. So you're just going to talk about this. So over here, this is how it's described, that so about it's about the withdrawing effect of Cedal bond O, which weakens or stabilizes the anion. For phenol or for ethanol, it's the weakest. Why? Because there's an electron donating alkyl group, which destabilizes, or you have an unstable ion. The negative charge density is a lot higher. And Mark 1 was for that, and you had to add this one as well, which is phenol is stronger than. There was 1 mark for this one as well, which was why are phenols stronger? Because there is electron withdrawing effect in phenols as well compared to alcohols, because when it ionizes, the electrons overlap with benzene's electron cloud, making it stable. So let's continue with this paper. I've posted the paper here, and let's continue tomorrow then. Okay.
Thank you, sir.
Thank you.